Hello everybody. Um, I'm going to do my version of a video on AC node solutions type stuff. There should be recordings of this on Dr. Scromy's channel, but we're going to approach this a couple different ways because I feel like the thing that is catching students is in the analyzing of complex valued matrices. But I would like to record a complete video on this, so I might actually split this into two parts so that we can just talk the matrix part in a separate video if that's all you need. But I am going to start this off so we can see where the matrix comes from. Oh, sorry, I haven't placed the ground as required. So I'm a little distracted trying to record at the same time. So one trick that I think is wise is going to be to place so for a nodal analysis here, we want to place the ground in the place that on a node that is connected to as many independent voltage sources as possible, just so that I don't have to write a super node equation. And so out of all of the places, this node right here is attached to both of our voltage sources. And I will do this even if the end I place it at puts us at the negative side of something. I kind of wish we had one. Um, Giving you the KCL equations to save me time. Voltage constraint equations, control variable equations. Oh, well, then I shouldn't have placed it somewhere that. Anyway, it's fine. So, all right, so it wrote some voltage constraint or some KCL equations. All right, so let's um, fill in some equations here. And if you see this video and there's something else you need me to record, send me a Canvas message and I can probably record something else today or tomorrow. All right, so we need a couple voltage constraints. So select the voltage source for open to write the equation. Yeah. Oh, okay. Sure. Okay, V1S. Okay, so I may have to re-record this. Let's see, it doesn't like that. An index number. Oh, right, yeah. Sorry, I'm being silly because it's supposed to be V1. It's equal to whatever V1S is because it's the positive side. So that's 5 angle 0. So we'll just throw that in there. 5 angle 0. Hopefully the clicking and typing noises are reduced by my, I'm using Crisp, right? I think so. Yeah, okay. Slightly clean up all the extra noises there. I think that's the equation it wants. Sure, so okay, then this one places a constraint on V2. So what's nice though, there is still now you just get simple equations. Then we get it's still, which is still worth it, yeah. So we don't have to write a supernode. So V2S here is going to produce a voltage of V at V2 equal to whatever V2S is, which is 4 angle 150. So we'll throw that in there, 4 angle 150. Check the equation. All right, and then we have one sought variable equation that it wants. Sought variable is a branch current. So we sought branch current. Okay, and conveniently the current is through something with one end at ground. So the IO that we want is just a voltage V3 divided by 6 ohms. Check. That should be it, right? clear fractions or cancel common factors. Okay, so we need to get all of our rows in terms of 1, 2, 3. Sure, so 1v1 is equal to 5 angle 0. v2, 1v2 is equal to 4 angle 150. And then, okay, so v1 over, okay, so I'm allowed to multiply this by 90. Okay, so if I multiply by 90 ohms, V1 is going to be 10 or minus 10. So actually, I'm going to move this part to the other side. So we'll make this. Yeah, okay. I mean, is that, sure. So, okay, so instead of 180 degrees, I'm going to make it minus 60 degrees. So I'm moving the 2 to the other side. So then V1 is negative 10. I just want to keep the signs over here the same. Take the ampere part, move it to the other side. So 2 is 2 angle 120 becomes 2 angle minus 60, or 2 angle, if you add 180 to 120, so you could do 2 angle 300, that's fine too. But I did minus 60. Okay, so I'm multiplying, oh, but I'm multiplying everything through by 90, so I can't forget that that's going to give me 90 times 2 is 180, which is fine. I just want these to be whole numbers, basically, if I can manage it. So V2 is negative divided by 5, so multiply that by 90. 90 over 5 is 18, so that's minus 18. Okay, so then for V3, I'm going to type it in. It's going to get mad, but I just want to keep track as we go. So the 5 is going to give us an 18 positive. 1 over minus j is j, so that's going to give us plus 18j, and it's not going to mind that either. And then V3 over 9 gives us an additional 10, because again, I'm multiplying by 90, so dividing by 9 gives me an additional 10, so this is going to go up to 28. And then V3 over 6, 90 divided by 6 is 15. So we need to add another 15, so that'll take us to 43. So we'll check the equations. Okay, then I need to convert them to a matrix equation, which seems pretty straightforward to me. Minus 10, minus 18, and then 43 plus 18j. Okay, then this is 180 angle minus 60, 150, 4, 5, 0. All right, then it's a matter of finding the answers. So, on a test, I will probably try to avoid giving you more than a 2 by 2 matrix where you could, I'm not guaranteeing this, but my current plan is if I set up a problem like this, you're only going to need a 2 by 2 matrix, and then you can bring with you the formula for the inverse of a 2 by 2 matrix, and then it'll be pretty easy. So you might want to do at least some of these by hand just for practice, but what I'm going to do to get my answer before I end this version of the video, oh, and it's only been almost 10 minutes. Okay, this could be worse. So to find my solution to this, I'm going to set up a matrix. If you don't have MATLAB installed already, you might consider doing that. Here's my ongoing process of trying to create a machine learning algorithm to solve Wordle because I find that amusing. I've barely done anything on it. I started doing this like a month ago. Anyway, other than that, we're going to actually try to solve the problem that we're dealing with. So I'm going to set up a coefficient matrix. And so I believe the matrix started 1, 0, 0, use semicolons to go to the next row, 0, 1, 0, semicolon again. So I'm going to have to run back and forth. So it's minus 10, minus 18, and like 43 minus 8, 43 plus 18j. Pretty sure MATLAB won't let you write 18j without a times. We might try to find out in a minute. Oh, I put a semicolon at the end to suppress the output, but I would like to make sure I didn't do anything too silly. So there's 1, 0, 0, 0, 1, 0, minus 10, minus 18, 43 plus 18j. Let's find out if, okay, yeah, MATLAB doesn't mind. Okay, but I still usually put the times in so that I don't forget to put the times in other times. Anyway, so there's our matrix, and then we just need to write our coefficients. And you can punch them into your calculator too. 5 at an angle of 0 is 5. Oh, so I'm going to call this B. 5 at an angle of 0 is just 5. And specifically, I know this because it is 5 times e to the power of j 0. But I know that's going to give me 5. The next column, game time pause. Yes, I'm here. I'm trying to show a video. All right. So then the next one is 4 angle 150. And I can absolutely calculate that out because that is a known angle. So that's like pi over 5 pi 6. So I would take the real part is cosine of 5 pi 6 times 4. And the imaginary part is sine of 5 pi 6 times 4. So you can calculate them manually that way. One of the issues that you might be having with solving with your problems in on a calculator, you got to watch out for your degrees versus radians. Your calculator is going to misbehave if you try to put complex exponentials in while you're in degree mode. So I do all my stuff in radian mode. The alternative is to manually calculate. Dr. Scromie showed you a method where you store e to the pi over 180 to a letter in your calculator. And then if you just raise e to the pi over 180 to the angle in degrees, you will get the correct complex number at the end. The reason for that is I'm going to calculate it the more direct way in MATLAB, where it's 4 times e to the power of, the angle is 150 degrees. So I'm going to convert that to radians as pi over 180. MATLAB will allow you to use the degrees to radians function if you're using MATLAB, which is actually a little bit easier, but not by that much. But at any rate, the next row is for e to the power of 150, or sorry, it's got to be j 150. J times 150 times pi over 180, which is 5 pi 6, as I mentioned. But I'll calculate it directly, and then something moved on the back of one of my screens as though it just gave me another time warning here. And then the final, yep, that's what it did, is the final column is 180 and an angle of minus 60. So that's 180 times e to the power of, I've already forgotten the angle, minus 60. Negative, negative j 60 times pi over 180. Pi radians in 180 degrees. You can use 2 pi over 360, 2 pi radians in a full circle, so 360 degrees in a circle. Oops, I need to close that, and I don't want to suppress it, so then we get this expression for b, and it's writing it, this is like 1 e to the 0.2 means it's 100 times this. So this looks correct. We just have very large coefficients in our third one here. What's nice in MATLAB is you can now calculate your solution. So I'm going to call the solution equal to v, and I can calculate it just as a to the minus 1. It might, or you can go like inverse of a times b. And if I don't suppress it, we get an answer. Okay. Which is fine. So then we have to take this back to rectangular form. So if you take it out to 4 decimal places, so MATLAB even has special functions of this, so we can get the magnitudes of V and it'll even let us go angle of V, which is kind of cool. This is in radians, so then you would go deg angle V equals rad 2 degrees of angle V. So there you go. And so it's just a matter of plugging those values in. Where'd Circuit Tutor go? It's over here. So our first one, though, of course, we already kind of knew most of these because this was in the form V1, V2 equals. So obviously our first couple solutions are 5 angle 0 and 4 angle 150. So now I just have to go snag the other values here. And so in MATLAB, we're looking at oh yeah, 3.0641 at an angle of negative 79.7843. I think I remembered that number right. 6 digits is starting to get past the number of digits I can remember. And we'll check those answers. Oh, then we got to compute the sought quantity. All right, so the sought quantity is I0. I0 is calculated as V3 over 6 ohms. Yes, you just divide the magnitude. So fortunately, this is just a constant, so we would divide it by 6. I can even get it out to full accuracy if I just call for absolute V, and I want element 3. Technically, you might go 1 comma 3, but MATLAB does some tricky stuff. It knows what absolute value of 3 is, abs v of 3 is. And so we're taking that divided by 6 ohms, and oh yeah, no, it would have to be 3 comma 1. My mistake. But I don't use MATLAB too much now, although I should have remembered what order to drop them. So it's 0.510724 significant figures. It had a lot more significant figures than that in the MATLAB calculation. So it's 0.5107 at an angle of the same angle, minus 79.78. I want it to full accuracy because I feel like it. So the angle is 7843. Check. And then in the time domain, all right, I'm not going to be super accurate on this one. So then all we have to do is go back to the time domain. So this is 0.5107. Assume that angular time frequency is 5 kiloradians per second. So you just drop the angular frequency in, and then minus 79.78, just as it says. Well, there you go. All right, so there's the solution. Now, I'm going to post this. This is the process you're going to follow. So, I will also record a separate video. I'll just put this in a double playlist again, where I'm going to analyze exactly this matrix. So I might do one where I intentionally don't put the ground in the ideal place. Then you might have multiple coefficients that you have to take care of. But yeah, anyway. So I'll probably run this one. I might pick a different problem, but I'll take a look. So I'm going to cut the video here. Have a good day, everybody. Bye-bye.